Hi students, today we are going to discuss about the another application of interference, which is air wedge. Okay, so air wedge, which we have already conducted an experiment in our lab. Okay, so you have seen the pattern. So air wedge is actually an arrangement which is used to check the optical flatness or the optical plainness of a surface. Okay, so the working principle behind this thing is this arrangement is interference. So actually the air wedge is looking like this. We have two glass plates. These two lines is representing two glass plates. One is AB and the other one is AC, which is separated by some kind of object, any very thin object. And you can see in between these two glass plates there will be an angle, small angle theta formed between these two glass plates, and air will be filled inside this two glass plates. So there will be a wedge-shaped air film between the two glass plates. That's why it is known as air wedge. Okay, since this angle theta, we know that 1 degree is equal to 60 minutes, and usually this angle theta is always, it will be less than 10 minutes. Okay, it will be around 3 to 4 minutes. In our lab while conducting experiment, it used to be 3 to 4 minutes. Okay, so that much very small angle theta is formed between these two glass plates. And the interference pattern of this air wedge, is actually okay. So interference pattern of the air wedge is, it is looking like this. Okay, so we are using sodium vapor lamp to illuminate this particular arrangement. So sodium vapor lamp has this yellow color, so it is pattern is basically looking like this. Here you can see this is one glass plate and this one is another glass plate, which is separated by some object of thickness E. And if these two glass plates are optically plane, you can see the pattern of the fringe pattern like this. You can see alternate dark and bright bands, and all these dark bands and all these bright bands have uniform thickness, and it is having a constant bandwidth. So what is bandwidth? So I told you that suppose this one, I have a pattern like this. Okay, this is my dark band and this is my bright band. The distance between adjacent or consecutive dark bands is, or the consecutive bright bands is known as the bandwidth. Okay, the distance between the adjacent bright bands or the dark bands is known as the bandwidth. Okay, so that is how it is looking. We have two optically plane glass plates. If it is not optically plane glass plate, we will never get a pattern like this. Okay, so we by the principle of interference, you can see here when the light is incident on this particular arrangement, and whenever we are doing the experiment, we always make sure that it is normal incidence to avoid the more complications. Okay, for normal incidence, we are using a wooden arrangement with a glass sheet so that it is incident normally into the air wedge arrangement, and we can see a beautiful pattern and we can measure the bandwidth. Okay, so when light is incident, monochromatic source of light is incident on this pattern, we will be getting a band structure, fringe pattern like this, the alternate dark and bright band. So in this experiment, so we it is not we don't need to derive the condition for the destructive interference or constructive interference, or it is not required to derive the equation for the path difference. Everything is given. We need to derive the equation for the angle theta. Okay, so here we have an angle theta. This is our angle theta. So we need to derive the equation for the angle theta between these two glass plates. Okay, so here we have the condition, that is, I told you the bandwidth is the distance between any adjacent dark band. Here we are considering the case of the dark band. So we have the condition for the dark band, which is 2 mu t cos r is equal to n lambda, where n is equal to 1, 2, 3, etc. Okay, so here mu is the refractive index, and in the case of air, the refractive index is 1. T is the thickness of the film. Okay, this is different. Okay, because we have a structure like this, right? So here we have one thickness T1 or Tn. Here we have another thickness, that is Tm. So as we are moving away from this point, we can see that thickness is reducing. Okay, so it doesn't have a constant thickness. So as we are moving away from the object, so here you can see, okay, this is our object. E, this one with the thickness E is our object. And you can see as we are moving away from this object, so here it is having another thickness, let it is x. Here it is having another thickness y, and here it is having another thickness z. And you can always see that x is greater than y and y is greater than always z. That is actually when we are moving away from this particular glass plate or obstruction, we can see that the thickness is gradually reducing. And here we have the equation for the condition for the dark band, which is 2 mu t cos r is equal to, this is equation 2 mu t cos r is equal to n lambda, where mu is the refractive index, angle is r is angle of refraction, n is the order, lambda is the wavelength, and t is the thickness. Here this n changes with respect to the thickness, okay, because the lambda is constant, r is constant, t is constant, mu is constant. So only thing that changes is the thickness, and corresponding to different thickness we will get different order of the band. So let's derive the condition, let's derive the equation for the angle of the wedge. For that I have this particular arrangement. Okay, I have this particular arrangement. In this arrangement you can see AC is my glass plate, AP is my another glass plate. Okay, here I have an object. I haven't mentioned the object. Okay, so here this BC is the width of the object or thickness of the object. Okay, so I have the thickness BC is the thickness of the object, which is T2. Okay, BC is the thickness of the object, which is T2. We are getting so many bands, right? So for me, I'm assuming that my nth band is formed here. Okay, my nth band is formed here. This is my nth band, and my n plus first band is here. Okay, my nth band is here and my n plus first band is here. So what will be the distance between these two? N and n plus 1 is adjacent dark band. So the distance between these two will be bandwidth beta. Okay, and from origin I'm mentioning. Okay, this thing from origin. This is my origin. Okay, A is my origin. From origin to the nth band, the distance is L1. Okay, while using the microscope, you can measure the position. So from origin to this nth dark band, my distance is L1. And from origin to my n plus first dark band, the distance or the position location is L2. Okay, the origin to my nth dark band, the position is L1. The origin to my n plus first dark band, the distance is L2. Okay, so that is all about this picture. Also, I have, this is BC, which is T2, I have mentioned here, and I am taking the thickness corresponding to the nth band. The thickness corresponding to the n plus first band is T2, which is BC. Okay, the thickness corresponding to the nth band is T1. Okay, which is ED. ED is equal to T1. Okay, so this BC is corresponding to my n plus first band, and this ED is corresponding to my nth band. Okay, so BC is T2 and ED is T1. Now let's derive the equation. So we are going to derive the equation for the what? We are going to derive the equation for the angle of the wedge. So as I mentioned, the same figure here. So as I mentioned, the thickness, the BC is BC equal to T2. Okay, and I'm mentioning this is my n plus first dark band, and this is my nth dark band. Okay, this is my nth dark band and this is my n plus first dark band. So the thickness correspond to nth dark band is T1. Okay, the thickness correspond to n plus first dark band is T2. So that's what I'm mentioning here. This BC is equal to T2 and ED is equal to T1. Okay. Also, I have already mentioned that from this point to the nth band the distance is L1. From this point to the n plus first band is L2. Okay. So A to D is L1. A to C is L2. So I am the nth band at a particular length AD is equal to L1 and n plus first band at a particular C is equal to L2. Okay, BC equal to T2, ED equal to T1, AC equal to L2 and AD equal to L1. Okay, now you see, okay, here we got BC, AC, ED and AD. Okay, now consider this, we have theta. We know tan theta, which is equal to, tan theta is equal to what? Opposite side by adjacent side. So here tan theta is equal to ED divided by AD, which is equal to also BC divided by AC. Okay, tan theta is equal to ED divided by AD equal to BC divided by AC. Also here you can see a small triangle, that is also theta. Okay, so that tan theta, the small triangle BF divided by EF. Okay, this one, for this particular triangle tan theta is equal to BF divided by EF. Okay, so now we can see tan theta is equal to ED divided by AD, which is equal to BC divided by AC, which is also equal to BF divided by EF. Okay, now ED is equal to what? ED is equal to T1 divided by L1, which is equal to T2 divided by L2. Okay. Now BF is equal to BC minus CF. Okay, BF is equal to BC minus CF. CF is equal to ED. So we can write BF is equal to T2 minus T1 divided by EF. This is EF, which is equal to L2 minus L1. Okay, so tan theta is equal to T2 minus T1 divided by L2 minus L1. Now when theta is very small, tan theta is approximately equal to theta itself. Okay, now we are considering that is theta is equal to T2 minus T1 divided by L2 minus L1. Okay, so this is my bands. Okay, so here this is my nth dark band and this is my n plus first dark band. Okay, so from here to here, okay, from origin to this particular point my distance is L1. So origin to this particular point my distance is L2. So this distance is known as beta, which is equal to L2 minus L1. So this distance, so we can rewrite this equation. That is, theta is equal to T2 minus T1 divided by L2 minus L1, which is representing the bandwidth. That is T2 minus T1 divided by beta. Okay, so theta is equal to T2 minus T1 divided by beta. Now what we are going to do is we need to find what is this T2 and T1, because without the picture, without the figure, this one, without this particular figure, our T2, T1 is irrelevant. So we need to find the value of T2 and T1. For that, we have the equation, general equation for dark band 2 mu T cos R is equal to n lambda. Okay, and for normal incidence, when doing the experiment in the lab, we are following this particular thing. We are following the normal incidence method. Okay, cos R is equal to 1. For normal incidence, cos R is equal to 1. Therefore, the equation reduces to 2 mu T is equal to n lambda. That is the general equation. Okay, so this is the general equation. Now, in this case we have nth band and n plus first band. For nth band, 2 mu T1 is equal to n lambda, and for n plus first band, 2 mu T2 is equal to n plus 1 lambda. Okay, 2 mu T1 is equal to n lambda and 2 mu T2 is equal to n plus 1 lambda. Now, this is my equation number 1 and this is my equation number 2. Okay, so I'm going to subtract this. Okay, I'm going to 2 minus 1 so that I can find the value of T2 minus T1. So I have 2 mu T2 minus 2 mu T1 is equal to n plus 1 lambda minus n lambda. Okay, 2 mu T2 minus 2 mu T1 is equal to n plus 1 lambda minus n lambda, that is 2 mu into T2 minus T1 is equal to n plus 1 minus n lambda is common. Okay, n cancels, that is 2 mu into T2 minus T1 is equal to lambda, and T2 minus T1 is equal to lambda divided by 2. Okay, so from the equation of the dark band we have T2 minus T1 is equal to lambda by 2 mu. This is what we are going to substitute into our equation. So here we have T2 minus T1. So we have T2 minus T1 is equal to T2 minus T1 is equal to lambda divided by 2 mu. Substituting this, we will get theta is equal to lambda divided by 2 mu beta. Okay, theta is equal to lambda divided by 2 mu beta. That is the angle of the wedge. Angle of the wedge theta is equal to lambda divided by 2 mu beta. In the case of AF, mu is equal to 1. Therefore, theta is equal to lambda divided by 2 beta. Okay, this is the equation for the angle of the wedge. Okay, now this experimental arrangement, we already conducted the experiment. So while doing the experiment, we have the source which is sodium vapor lamp. Okay, which is used to illuminate the air wedge, and we will be placing some wooden arrangement so that it will make a normal incidence. Okay, this arrangement is just for normal incidence. And the telescope is here so that we can look through this particular telescope and we can see the pattern. Okay, so that is the experimental arrangement. So the application of this air wedge is, suppose we are using the optically plane glass plate, optically plane surface, we will get a uniform band structure. We will get what is a dark, alternate bright and dark bands of equal thickness and with a constant bandwidth. But if suppose we have a convex surface, that is we have a projection like this, the band will be something like this. There will be a shift towards the left side. And the same time, if we have a concave like this concave, the band will be little shifted towards the right side. Okay, only for the optically plane surface we will be getting a pattern like this uniformly arranged alternate dark and bright bands of constant bandwidth. Okay, this experiment is used to check the optical flatness or optical plainness of a surface. Okay, I hope you have an idea about the air wedge experiment. We already conducted the practical session. Go through this video and study this, because this is one of the important essay question repeatedly asked in the university question paper. Thank you.